Hello and welcome back. We have been talking about the pedagogy of the introductory programming course, and we were discussing how we should teach the introductory few lectures. So I want to talk about what should we be telling students about computers as an introduction. So let me begin by saying what I think we should tell students about how computers solve problems. So we want our students to believe that computers are very useful. So what we should do is we should show them some interesting computations, and we should explain to them how computers work on those computations at a very high level, sort of like a popular science level. So some examples that we could do are image processing, text processing, maybe weather prediction. These are my favorite examples. You could have your own and you could develop your own as well, but these examples are also developed in the book that we have been mentioning. Okay, so what should we be explaining about these examples? Okay, so first of all, we should say that when a computer solves a problem, everything has to be represented as a number. So whatever questions we ask should be phrased in terms of numbers. Okay? So for example, if we are talking about text, then we are going to represent text by numbers, or in other words, for every letter we are going to have a numerical code, which as we know is the ASCII code. If we want to do image processing, again we should first convert our image into numbers. How do we do that? Well, we divide the image into small squares or pixels, if you will, and for each pixel we associate a number which is equal to the intensity of light at that pixel. If it's a colored image, then of course we'll have to talk about three intensities, the red, blue and the green intensities. But the point is that information about colors and parts of images can be represented in terms of numbers, and that is what you need to do if you want to process numbers and pictures. Now about weather prediction, okay, we can say something like the following, that again here we are going to discretize. So we are going to take the map of the world and we are going to put points on it, and we are going to say let us put variables for different points. Okay? Okay, so once you express everything as a number, we can apply laws of physics or somehow get the relationship between numbers and ask questions about the numbers, or we can say here are the equations that these numbers had better satisfy, and so we solve them. Okay. Now what is an algorithm? Well, an algorithm is a precise description of what calculations are needed, and right now I am talking about a manual algorithm, and these will be, say, English language descriptions of what do we do with the numbers that we just constructed. Okay, so maybe we are setting up equations, we are solving them, whatever it is, but that's what we have to say. Here we could say that look, we should give an introduction to algorithms and what the term algorithm means as well, and not only that, we should say that look, you really know algorithms. So right now, right then, in the very first or second lecture I suppose, we should tell the students that this is what an algorithm is and that you already know algorithms. Primary school arithmetic is nothing but an algorithm. Okay. And then we need to assure students that a computer can perform all the steps that are used in manual algorithms, and so whatever manual algorithm you have, we can somehow feed to a computer as well. So if in your manual algorithm you are doing some arithmetic, your computer will be able to do it. If in your manual algorithm you say that okay, if this is 0 then do this, if it is 0 don't do this, we will be able to say all that in the instructions that we give to the computer. Okay? All right, so continuing along that, we also need to tell a little bit about how a computer works, okay, to the extent that it helps in programming. Okay. So by this I mean the insides of a computer. So we have to say something like a computer contains memory, it contains some logic hardware, again at a fairly high level. Now, if you could say, you could use anthropomorphic terms that a computer is like a dumb human being or something like that. But, or you could say, you could try to give a view which is more realistic. Okay? Engineering students, I think, will like a realistic view if they can understand it. And in fact, that is what is done, and that is what I recommended, and it is done in the chapter 2 of this book. If you give a realistic view, the chance of misunderstanding it is less. Okay, so how do computers work? So a notional view, okay, could be that a computer circuit understands C++ programs. The difficulty with this is that now students tend to think of computers as human beings, and they associate human attributes with computers. So human beings have common sense. They start thinking that computers have common sense. So you have to be very careful with notional views. You have to somehow give the feeling that computers are like human beings, but they are also not like human beings. And this is a little difficult. On the other hand, here is what a realistic view might be, and it's discussed again in the chapter. You could say that a C++ program is translated into a machine language program by a compiler. After all, you are going to tell them what compilation is, so you might as well tell them that, look, the output of the compilation is machine language. Then you could say that a machine language program is a sequence of numbers representing actions that the computer must perform. So you might say, you might ask me, look, don't we talk about machine language in the computer architecture course or computer organization course which comes later? Of course you do. Of course you talk at that point. But here it's just going to be something in principle at a very high level. And the reason for doing it is to have some clarity. The details are not important. The reason for that is to have some clarity about how a computer executes. So this will clearly tell the student that a computer is not like a human being. Okay, so it has to have this very peculiar input which consists of numbers. So you could say, for example, that 70, 30, 31, 32 could mean add the contents of location 30 and 31 and place the result in 32. So 70 somehow means addition. Another example, 80, 30, 31, 32 might mean multiply. So instead of 70 we have 80, and that changes the add to the multiply. So this is something that students actually enjoy. Okay. So note that these are engineering and science students that we are talking about primarily, but even other students will enjoy this. They like codes, so they will understand, and they will have fun with this. But the more important part, of course fun is important, but there is also a more important idea. And that idea is that a computer needs to be told in a very specific kind of a manner what we expect it to do. Okay, so the moment you start with these kinds of codes, then students understand that, look, the codes are important. The codes are, I mean, they are not going to come out of thin air. So somehow you have to do something which will cause these codes to go. Okay. Now, in addition, of course, you should say that your program must contain every action that you want performed in exactly the order in which you want performed. Okay. But the moment you say that instructions are of these numerical types, you are sort of telling the students that, look, the computer needs to get very precise information told to it. Okay, so let's continue this discussion between the two ways of describing. So if I want to talk about a variable, there is a realistic view which says that when you write int xyz, what happens is that you get 32 capacitors in your computer memory for storing the value of xyz. Okay, so note that I am not saying you always get 32 capacitors, but you typically get 32 capacitors. These days saying you always get 32 capacitors is not wrong, because actually your computer memory does consist of capacitors almost entirely. So, but you can play it safe and you can say that no, it could be a little bit slightly different once in a while. But this is actually what happens, that xyz becomes the name that you give to a portion of your memory, and int is typically 32 bits long, and so you get 32 capacitors. What is the notional view? You could say something like a variable is like a box into which you place the value. Now, this is a fine description, but it is amenable to misunderstanding. Okay? And this has been studied by many researchers. So, the references are at the end of the slides. And for example, a variable can be thought of as containing several values simultaneously. Why? Because if it's a box, well, I can put several slips of paper in it. So, if I write a equal to 1 and then I write a equal to 2, well, maybe the second slip of paper got in. Okay. When you execute x equal to y, the imagery that perhaps this conjures up is that a value moves from y to x. Actually, that's not what happens, right? Nothing goes out of y. The value in y is copied. So, if it is capacitors, then the notion that the value sort of moves is harder to imagine, because you will say that, look, why should the capacitors relating to y, why should they change? Okay, so that would not be the natural way of thinking about it. So, here you could say that, oh, the paper moves. And this is another interesting misconception that students can create, which is that a variable can contain not just a value, but it can contain a formula or an unevaluated expression. After all, it's a box into which you are going to place a paper on which a value is written. Why not place a formula? And here is a more detailed example that one of these authors discusses. So, suppose you give this information to students. The number of children is the number of girls plus the number of boys. How many children are there if there are 7 girls or 5 boys? Okay, actually it's a different author. So, the way you would represent this information is, you would say in children, boys, girls. So, okay, so the number of children is an integer, the number of boys is an integer, the number of girls is an integer. The number of children is the number of girls plus number of boys. Okay, so children equal to boys plus girls. Okay. Now, this is not a good statement. The boys and girls have to be given values first, and only then can this statement make sense. But students do write this statement because it appears first in the order in the English language description. And here they think that, oh, children, the box corresponding to the children will get the formula boys plus girls. And later on they can write boys equal to 5 and girls equal to 7. And now that box, the formula in the box will be modified. Okay. Now, all these misconceptions are very unlikely, or less likely I should say, with capacitors. So, clearly if there are capacitors and if you have told your students that each capacitor stores a 0 or a 1, certainly a formula will not go in there. Okay. So, basically the point is that we have students who have studied some amount of science, who understand what a capacitor is, and to them you should tell that a memory is made up of capacitors. This will satisfy their curiosity, but it will also reduce the likelihood of misunderstanding. Okay, so what kind of homeworks can you give on this topic, in the introductory topic in which you describe how computers work? Well, you could say, describe in words how you multiply n-digit numbers. So you have assured in the first part of this that you have told the student that multiplication is an algorithm. So now you ask them to work that out. How exactly do you multiply? So here you should tell the student that you should expect to think about how many phases there are, what happens in the ith phase, are there nested phases, okay? And you should write that down. Why? Because that description is going to help them in writing a program to multiply very large numbers. You can tell them that if you have very large numbers, computers will typically multiply them exactly using the high school method. You could ask, what happens if you execute the instruction 70, 30, 30, 30? Okay, here of course this should come immediately after you tell them what 70, 30, 30, 30 means. So it's not a test of memory. Okay, but here what is going on? Here a square is being calculated. So then you could ask, what if you execute these two instructions one after another? So you square twice. Well, so what happens? The fourth power gets calculated. So what you are trying to do in this is that you are saying that what I have told you are elementary ideas, and those elementary ideas can be composed, and from that composition something bigger can be constructed. So that's sort of a big message that you are sending. But a smaller message that you are sending is that you are testing whether they understand, whether they are with you. It's not that they need to remember what 70 means, but if you just told them what 70 means, and if you told them this structure, then they should get this. They should start thinking in this manner. So basically, this homework should be reinforcing the idea that computers work mechanically. They don't have common sense. They have to be told everything. Now, the way most of our courses work is that there is something that happens in the classroom, and what I have said, these homeworks could happen at home, or maybe these are assignments that you give to students to check their understanding. But then you also have programming labs. What do you do then? Now, this is the time where you can ask them to do more drawing programs. You have just done turtle geometry, you have shown them what the turtle can do, and now you can get them to write those homeworks or more complicated drawing programs. And the book certainly gives many ideas, but I'm sure you will have many ideas. So just using repeat, left, right, and repeat is key over here, you can draw very interesting and intricate pictures, and we have seen some of those, and I'm sure you will think of more such pictures. The second topic that typically gets taught is about data types and variables and assignment statements. Operator precedence, rounding, truncation, all of these things have to be taught. In some sense, there is an information overload. So a natural question is, can we make this learning active? By active learning, I mean students have to think, students have to participate somehow. If you just keep feeding information, then you know what happens. Students may have their eyes open, but they might actually be sleeping for all practical purposes. We don't want that to happen. If at this point you ask students to write programs, there isn't much you can do. If you use the standard teaching style, what is the most interesting program you can ask? Well, you can say, I weigh 150 pounds, whatever. So what is my weight in kilograms? So they read in the number, they store it into a variable, they divide it by 2.2, and then they print the answer. So all these things they can do because they have just learned. But nothing much more. Remember that they don't even know the if statement. However, you have to keep in mind that students will remember concepts better if they are used for doing interesting things. If you do interesting things, if you tell good Panchatantra story, then students will know moral principles better. If you just tell them moral principles, no story, nobody remembers. So you have taught them assignment statement, you have taught them very interesting ideas, but they have to be used with some interesting stuff if you want the students to remember them. Now with our approach, students already know repeat, and therefore many interesting programs can be written. So what can you write? So we can draw more interesting pictures. For example, here is the code to draw a spiral. So we start with int I equal to 10 and then repeat 10 times. Forward I, right 90. This is almost like drawing a square, but after each right 90 we are going to change I. So what will happen? So first time we will go forward 10 pixels, then we will turn, and after that we will go 20 pixels. After that we will go 30 pixels. After that we will go 40 pixels, and so on. So this won't draw a square, but it will draw a spiral. Okay. Now here is an important point. I equal to I plus 10 is a very interesting statement. It's a very confusing statement as well, because students have learned math in which equal to means one thing and equal to means something quite different over here. So if I show I equal to I plus 10 to somebody who doesn't know programming, they will say, well, cancel I from both sides and we get 10 equal to 0. So this is nonsense. But by writing this statement, we are reinforcing the distinction. We are saying that, look, in this figure, if we want I to change in this manner, we have to write the statement, and what the statement does is it takes the old value of I, adds 10 to it and places it back in I. Okay? So this is a very important picture to drive home the fact of self-assignment or reassignment, but especially dependent on the old value. Calculate averages is another example which is also being discussed in the chapter 3, where assignment statements are discussed. So what happens over here is that we are going to read in numbers. We are going to read in n, which tells you how many numbers we are going to read. We are going to set sum to 0, and in each iteration of the repeat, we are going to read a number and add it to sum. And finally, we are going to print out sum divided by n. So of course, this assumes that the number of numbers that we read is greater than 0, but barring such points, this is pretty good code. And notice that it's probably the simplest code. If you use a standard looping construct, you would need an additional variable to count how many iterations have happened. Over here, repeat n sort of hides that, and because the code is simple, I think the students have an easier time understanding this piece of code. Now, as far as the assignment operation is concerned, I said already that it can confuse students with the equality in mathematics. So several trivial points need to be hammered into students. Okay? And this is another example of how computer computation is different from human computation. So this was one theme of in our second lecture sequence, I should say, of that computers compute in a different manner in some sense from humans, although analogously different, but different nevertheless. But here is sort of a more low-level manifestation of the same principle. So specifically, equality, when we talk about it, might mean equality, mathematics equality. Okay, and when you say equality, it might mean some kind of comparison, whereas on a computer, equality typically means assignment. And this confuses every student who learns programming. Or maybe it doesn't confuse a few lucky students, but most students will get confused. Most students will write equality somewhere in their program to mean checking for equality rather than assignment, and that will make their program make a mistake. So in principle, you would think that this confusion is very superficial, it's only syntactic and so should be easy to avoid, but in practice that is not so, because the mathematics interpretation of equality is so well established that students who might be slightly inattentive in your lecture will get lost. So this is a point that you should say a few times. Look, I mean, we have to worry about students who are slightly inattentive, right? I mean, we are not attentive all the time, let's confess it, and our students are not going to be attentive all the time, and so we have to ourselves pay attention and see, are they attentive, are they not attentive, and sort of compensate for inattentiveness. Okay? And because equality in mathematics, equal operator can mean equality rather than assignment. If I say the number of boys plus the number of girls equals the number of children, okay, on one hand it's a statement of mathematical equality, but people may write it and people do write it as children equal to boys plus girls, meaning a formula. And so boys plus girls, the formula gets stored in the box for the variable children. And so these kinds of interpretations are invited also by this equality symbol. So again, as I said earlier, students might not just get confused by equality, but they might also use equality to mean comparison instead of using equal. There is a compiler option which will warn you. Okay, so if you write if A equal to B instead of A equal to B, and you use this compiler option and S++ is configured to use this compiler option, you will get a warning. Okay, so use that. Another point about operators is that division truncates. So I might write the following statement: centigrade equals 5i9 times Fahrenheit minus 32. So the value of centigrade will be set to this. Unfortunately, 5 upon 9 will be evaluated first, and that division is truncating. So many students are going to make this mistake, unfortunately. Okay, so this really, I think, is a language problem. The language should do something about this. In fact, Python has done this. In Python, if you write 5 upon 9, it doesn't mean 0. It means 1.8. So the division operator will have the result as a double. Okay, so if you want an integer, then you'll have to additionally change it to an integer. And I think the way programming languages evolve, I won't be surprised if C++ also changes this at some point or another. Okay, so we are going to take a break here, and when we come back, we will talk about program design. Thank you.